Okay, I'm going to try to show you circuit maker and the experiment number 6, a summing amplifier. Called it experiment number 6, op amp experiment number 3. So I've got circuit maker open. I'm going to open up the first circuit. I open up the first circuit. I'll blow it up. And what you see is I've got an op amp, I don't know if you can see the exact op amp here, a UA741. That's a typical op amp. It's got a feedback resistor of 5K. It's got power plus and minus 15 volts. It's got two inputs, I1 and I2, and they go into the negative or inverting input of the op amp. They're both 5 volt sources, V1 and V2. I take that back one, V1 is 5 and V2 is 3 volts. They both have 5K ohm resistors, R1 and R2. So what happens with a summing amplifier is I can put more than one input into the inverting input of the summing amplifier. The reason I can do this is what we call virtual ground. If you look at the circuit, it turns out that, and I'll try to zoom in a little bit here, we'll see how successful I am. If you take a look at the circuit, the op amp itself has a minus or inverting input and a plus or non-inverting input. And it turns out that all the integrated circuitry within the op amp causes the voltage between the minus and plus input of the op amp to have a differential of 0 volts. That is, they have to be at the same potential as long as I have a feedback resistor. And you can see there's a 5K RF there that feeds back the output from pin 6 of the op amp into pin 2. That feedback resistor, once it exists, it turns out that, again, the internal circuitry causes the voltage difference between the inverting and non-inverting input to go to 0. Now, if that's the case, pin 3, the plus input, the red one there, is at ground potential. Therefore, pin 2 also has to be at ground potential. That's where we get the term virtual ground. So, voltage source V1 and resistor R1 will cause a current to flow I1, and also voltage source V2 of 3 volts and R2, the 5K ohm resistor, will cause a current I2 to flow. Those two currents, using Kirchhoff's current laws, will add together and they form I total. I total flows towards pin 2, the inverting input, the minus input that's colored blue there. But it turns out that besides the virtual ground concept, we also discover that the internal circuitry of the op amp make the inputs look like they're high impedances. Therefore, no current flows into the op amp. Excuse me. Instead, they flow through the feedback resistor as current IF. So I'm going to take and run the simulation now. Okay, and of course we come up with an oscilloscope we don't need. And now what we see is the currents. So over on the left hand side, let me zoom out here. Oops. On the left hand side we see current I1, and current I1 is caused by V1 divided by R1, or 5 volts divided by 5K, which would be 1 milliamp. On the meter it shows it as 1000 microamps, which are 1 milliamp. Current I2 is 3 volts divided by 5K, which turns out to be 600 microamps. The 1000 microamps and the 600 microamps add together to get 1.6 milliamps flowing into the, appears to flow into the minus or inverting input of the op amp. However, what you see is the 1.6 milliamps actually flows through IF, the feedback current, and that'll flow through RF, the 5K ohm resistor. Ohm's law tells us that 5K times 1.6 milliamps will be roughly 8 volts. And it turns out that the polarity is such that it turns out to be minus 8 volts. Actually, the meter shows on the far end of this, the meter shows, I think, minus 7.999 volts, which you might as well round off to minus 8 volts. Okay? Now, that's the first one we do. So I'll stop that. Then I'm going to take and load the second circuit. Not going to save anything. So now we have a second circuit. In this case, it turns out that our two sources are a little bit different. We have a battery source of 1 volt plus 1 volt through a 5K resistor, and we have a 2 volt peak to peak 1 kilohertz sine wave applied through resistor R1 of 5K. The feedback resistor is still 5K ohms, and we're going into the minus input. Now this is a summing amplifier again. I can have more than one input. That virtual ground aspect allows me to take and put numerous inputs into the inverting input. So I have the 5K ohm RF and the 5K R1 and R2. I have a gain of 1 there, and it turns out that I'll have a replication of the 1 kilohertz sine wave, 2 volts peak to peak, and I will take and have 1 volt going through the resistor R2, which will give me a 1 volt output of DC, but they're both going into the minus inverting input. So it turns out that what we're going to see is the following. So I'm going to run the simulation, and let me blow this up. What we see is the, now by the way, let me make it a little bit smaller here. You can see that on the simulation, the yellow wave is the sine wave input, and B is the output from the op amp. So what do we see? Well, we see a 2 volt peak to peak yellow sine wave here. Then we see the output, and let me zoom back out here. We see that the output is the green waveform, and it turns out that it is a waveform that's 180 degrees out of phase with the yellow waveform. The yellow waveform is going up while the green one's going down. So we have a polarity reversal, and it turns out that the green waveform is centered at minus 1 volt. That's the battery voltage being inverted. So it turns out that we have an offset of minus 1 volt, and we get a 2 volt peak to peak sine wave at 1 kilohertz out. This is what the circuit should do. Then I think I change a couple things here. I think I take and I'll stop this, and I think I'll take and change the R2 to 2.5K. And so what should happen is the gain for the 1 volt battery now should be twice what it was before. So let's see if this is the case. We run the circuit again. We see our waveform, and lo and behold, what do we have? We now take a look, and if I bring cursor C down to about minus 2 volts, which is somewhere around here, just about there. Well, if I play with it a little bit, I guess I don't know if I think as close as I get is minus 2.005 volts. But we see that the sine wave now has been inverted, and it's also down with a offset of minus 2 volts. So that works the way it should. Okay, the last thing I'm going to do here is I'm going to take the 1 volt battery here. I'm going to edit it, so I'm going to make it minus 1 volt. So if I make it minus 1 volt, what should happen is the offset should change to a plus value instead of the minus value it's been. So let's see if that works. I run it, and sure enough, Now what you discover, the output, the green one, is centered at about 2 volts, and I can't get closer than about, 2.05 or something like that. So there, my sine wave has now been shifted to centered around plus 2 volts, or an offset of plus 2 volts. Again, if you think about a oscilloscope, there's a position control on an oscilloscope, and it turns out what I'm doing here is essentially the same thing that position control does on the oscilloscope. I'm adding voltage in to shift where the waveform is. Okay, so for the last circuit, I'll grab summing up number 3. I'm going to open this guy, and here's our new circuit. And this one now, kind of interesting, we have two, so I'm going to try to blow it up a little bit. Let's see if I can do that. We have 2 sine wave generators. Both of them are putting in a 2 volt peak to peak 1 kilohertz wave. They're both going through a 2.5 k ohm resistors. My feedback resistor is 5K. So let's take a look and see what happens. I should sum these voltages together. So I run this, and lo and behold, what do I get? My green output, which is the summation of those. It turns out, you may notice that it goes from plus 4 to minus 4 volts, or a total of 8 volts peak to peak. Remember, I started with 2 voltages that were 2 volts peak to peak each. If I just added them, I would have got 4 volts peak to peak, but I go back here, I got a 2.5 k ohm resistor here and here, which means I've got a gain of 2, because my feedback resistor is 5. Gain is RF over Rin. So I get gain of 2 for each of these, so I get a voltage out of 8 volts peak to peak now. So it works the way it should. I'm going to stop that guy. The next thing I think I do here is I take and modify this guy. I'm going to edit the signal generator, and I'm going to put in a delay of, let's see, 0.5, I think it's milliseconds. Of course, you have to always worry about I'll hit OK. And let's see, the units there may or may not take, we'll find out. So let's take and run this. So this takes 2 sine waves, and by the way, let's go back, let's make this small. See if we can get that small. Well, I'm not able to, so I'm going to take and make it real small. Well, I guess I got to, come on. See if I can make it small, or drag it down, one or the other. Okay. The blue and the yellow are the input waveforms, which are identical 1 kilohertz sine waves, except V2 starts a half a cycle after V1. The green is the output. So let's take a look now at our output here. So what happens? Notice that since all I have is the blue waveform going in, and I've got a gain of 2, what happens is the output is flipped over. It's the green waveform that you can see, the big one, to start this oscilloscope display. The yellow, which remember doesn't start the half a waveform's gone by, is 0. And then what happens is the yellow and the blue, which are out of phase by 180 degrees, cancel one another out, and the output goes to 0. So what I've achieved here is had a single half pulse on the output by putting 2 sine waves in where they're out of phase with one another. So this works the way it should also. So the last thing to do here is, I believe, we'll stop that, and I think what I do, or ask you to do, is to take and change this guy to a 10 kilohertz signal. So let's make that 10 kilohertz. Hit OK. Oh, and I'll get rid of the, I want to get rid of the delay. So just make it so there's no delay. I'll hit OK. And we'll run this guy. And what we see is this kind of weird waveform here. I don't know how well the colors show up on the camera. But we've added a 10 kilohertz. If I take and grab this and push it down, we've added a 10 kilohertz and 1 kilohertz signal. They should have the same amplitude, and their output should be the green signal. So again, the yellow one and the blue one are two different frequencies, and they add to give you this guy here, the green one. And that's what happens when I add signals together. Okay, so hopefully this has been helpful, and we'll see how it works.